Okay, I think it's better to start this one. This is number 31 from scratch. And I've identified all the forces on the ladder. And so this is the normal force of the wall, Fn2 we'll call that, and versus the normal force from the floor, which is up, we'll call that Fn1. And then this is the force of friction this way that keeps it from sliding. There's the force of friction. And then we have two weights pushing down. One is the weight of the person standing there that's 70% up. We'll call her M2G. And then the weight of the ladder itself, which happens at its center of mass, we'll call that M1G. M1G. So as with any statics problem, you just set all of the forces equal to 0 and then all the torques equal to 0. And torques is sort of the new thing. So the net force in the x direction should equal 0. And then I look at my diagram and I say, who are the x forces? So it's this force of friction is in the x direction minus this normal force from the wall. So force friction minus Fn2, those should add up to 0, which means the force of friction should equal Fn2. And let's just play that out. That means force normal from the ground, which is Fn1 times mu static, should equal Fn2. Okay. If I look at now at my y forces, those are going to be this guy pushing up from the floor minus these two weights pushing down, and I don't see any other y forces on my diagram. So those will be the 2, the 3. So it's going to be in the y direction, it's all going to add up to 0, and it's going to be Fn1 minus M1G minus M2G. So already I can see if I can solve this equation, this y equation, for Fn1 there, then I'm going to be able to plug that in there, which is important for finding mu, which is the goal of the problem. So I can solve this, and I put in all the values for the mass of the ladder, the mass of the person. They're going to combine and equal 284.2 newtons. Now what I can do is I can put that value now into my x equation here. So now I know 284.2 equals times mu. Alright, so we'll come over here. So we put this 284.2 newtons in for Fn2. Now, if I could figure out for Fn1, if I can find out Fn2, I can solve the problem and find mu. But I'm out of x and y equations, which means to find Fn2, I'm going to have to do something with torque, and that's going to be a little tougher. So we need to deal with the torque end of this equation. So net torque equals 0, and we look, and to define torques, you're going to have axis of rotation that you're going to decide on. So I'm going to pick right here as the axis of rotation, and the reason for that is what it does is it takes FF and Fn1 out of the picture as torques because they have no lever arm. So that means M1G, M2G, and Fn2 are my torques. So here's M1G, and the question is, where is its lever arm? Okay, and it's this distance right there. There's M1G's lever arm. If I drop this sort of down this way, this is the perpendicular distance. This is the perpendicular distance between the axis of rotation and this force because they meet at a right angle right here. So there's M1G. And similarly, if I drop M2G, let's use red for him. His perpendicular lever arm is this distance right there. That's his lever arm. And then for Fn2, I'll use red for him too. If I extend him out, his lever arm is this distance right there. Not very pretty, but there's the perpendicular distance. There's the lever arm for Fn2. Alright, so I'm going to redraw this out over here to the right, and you can see here is the lever arm for M2G, here's the lever arm for M2G. This is M1G, M2G's lever arm. And then Fn2, which is here, I'll just redraw that in black, and it is this distance right there. So there is the lever arm for Fn2. So now we need to do our torque equation. So positive torques are counterclockwise torques, and so for us then that means Fn2 has the tendency to make this ladder want to go counterclockwise, so it's a positive torque. M1G and M2G, see, make the ladder want to go around like this, which is clockwise, which is defined as negative torque for us. So this is the positive torque, torque due to Fn2, and then the negative torques are the torque due to M1G and the torque due to M2G. Right? But these are torques, not forces. So all this will add up to 0 since we're in static equilibrium. So a torque is a force times a lever arm. So this torque would be Fn2 times its lever arm minus M1G, that force, times its lever arm minus M2G times its lever arm. So that's as far as I'm going to go. I'll let you plug in the numbers, but Fn2 is what we want to find here. We want to find Fn2. Rn2 is this distance there, which in the problem tells you it's 4 meters. This distance here, the lever arm of M1G, would be half this entire distance, and they tell you that entire distance in the problem is 3 meters. That means this value here will be 1.5 meters because it'll be half this distance. And then this distance right here, they just simply tell you in the problem, is 2.1 meters. So now you solve this whole equation. The only thing you don't know is Fn2. Then you take Fn2 and plug it back in all the way back up here and solve for mu, and you are done. Notice one little problem here. I put, instead of 17 here, this should be 70. The painter was 70 kilograms, so instead of 284.2, that makes that 705.6 newtons. So this is 705.6 mu equals Fn2. So just make sure you make that correction. And if you fill all that out correctly, you should get an answer of mu equals 0.57. So then just filling in numbers from the problem, here's 0 equals Fn2, 1.5 meters is its lever arm. No, it's not.